Okay, so we've talked about what our eventual goal is with this, which is a static code analyzer. We've talked a bit about the theory previous, and now we're going to talk about the algorithms, because there's a couple of gotchas when trying to implement this data flow analysis with an actual algorithm that can quickly make the problem exponential, which in turn makes it intractable. So in here we're going to basically discuss different tools we can use in order to try and simplify the process. When looking at these algorithms, it's best to think about it from either a compiler standpoint or a static code analyzer standpoint, because they're trying to store what information they can in order to do some type of analysis on your code. So we've already talked about calculating definition use pairs, but one definition we need to get to is VD reaches U is a reaching definition if at some point it can reach U or get to U at some point. It reaches it. If control path passes through another definition, then it kills that reach at that point. Even if we consider only loop-free paths, the number of paths in a graph can actually grow exponentially larger than the number of nodes. So practically speaking, we have to come up with a way in order to simplify it. Let me give you a picture of why this is a problem. Let's say you have A, which could go to either A sub 1 or A sub 2, and then back to B. And B could go to, let me get my mouse pointer out here, B sub 1, B sub 2. C could go to C sub 1, C sub 2, so forth and so on. Well, how many code paths there are? Well, 2 from A to B, 4 from A to C, 8 from A to D, 16 from A to E, 128 from A to V. Hopefully you see that this is doubling, which would mean that this will quickly turn into an intractable problem for us. So we need to come up with different tools in order to try and simplify this process. And look, we're not even talking about adding a loop. So hopefully you can see with a loop, which iteration are we exiting would make this blow up even faster. So what we have, they call it the DF algorithm, data flow algorithm. Sufficient algorithm for computing reaching definitions for several, and actually other properties as well. Now, you'll see that we can extend this. Suppose we're calculating the reaching definition of node n and there is an edge p of n from an immediate predecessor. The thing to keep in mind is that if the predecessor of p can assign a value to a variable v, then the definition of vp reaches it. So we say the definition of vp is generated at p. So we can generate p, or vp. If the vp of variable v reaches the predecessor node and v is not redefined that node, then definition is propagated. All right, again, a picture I think really helps out with what's going on. So we're talking about reach and reach out. So if you're looking at E right here, notice we're saying calculating reaching definition of E in terms of the immediate predecessor of D. So you have E. Well, what gets to E? Well, it's whatever's popping out of D, right? Whatever can reach out of D is obviously the reach of E. Okay, well, hopefully that's at least, that definition makes some sense. Just think about that that should hold true for every sequential statement. And the reach out of E is basically the reach of E, aka the reach out of D, minus y of A, because we're defining y right here, so it's not pulling it from up here anymore from y of A. Y of A is being pulled here, so we're going to need to remove y of A because we killed it. And then we need to union it with our definition of y of A, of course. So y of E. So in other words, kill or get rid of the old definition of y of E and add our new definition of y of E to this list, is all we're saying here. But if you add a loop, this line has two predecessors, before the loop and the end of the loop. So you need to have the reach out of A because that's where it could come from top, and you need the reach out of E because that's where the loop could come around. So that's the reach, is just the reach out of those two lines. Of course, the reach out of A is where all these variables are generated. So x of A, or x at A, x at Y, and temp at A. So the reach out of A is just where this variable is generated. Of course, the reach out of E is what the reach is of E. Notice that we're subtracting old y of A because it got killed there and unioning it with y of E. Now this is a union, so it's going to involve all of those, namely y of A, x of A, y sub A, temp sub A, and y sub E as well, because we are unioning the reach out of A and the reach out of E right here. So general equations, hopefully you've seen a pattern. The reach is really just the union of the reach out of any predecessor. All right, great. The reach out is its current reach that you've calculated subtracting anything that killed at that statement, and then unioning it with anything that's generated or defined at that statement. Hopefully this is straightforward. If you're thinking about this from a static code analyzer, notice that while it may not know at this point what the reach out is, it might be able to move from this line, go to this guy, this line, and when we're down here, we realize that we need to update B with the reach out and probably go through another loop or iteration to detect all the reach outs here. And after you go through a second pass, all the reaches has probably been updated correctly, but you might do a third pass just to make sure. And then if nothing has been updated, continue on. And that's really how this algorithm is going to end up working. We'll show you that algorithm, of course, towards the end. But that's the reach. One thing we want to talk about is available. Available is simply what definitions can you know for sure are correct at this point. In other words, back at this piece of code, when you're at this line, you want to know what definitions can you use from here. Well, you can use the definition of x, because x is, well, use the definition of x here. Actually, you can't use the definition of x. That was a lie. You actually can't use the definition of anything because everything's overwritten. So let me come up with a better example. Sorry about that. If you're at this line, which definition can you use for x? Well, you know x was defined previously here, so you know you have the availability of x here. And the availability of temp is here as well. So you know what the values of those two are. The reason why you cannot know what's available here is you don't know if the value of x is defined up here or defined down here when you're executing this while loop. If you're at this statement right here with, or we'll say x equals y right here, you know again that you don't know if it's x sub a again or another iteration of the loop. So really the only value right here is that you know, well, you don't even know what y is. But you know here at temp that you're coming from the previous line of temp is really the only thing you've got. Hopefully, I know that's kind of confusing. In a while loop, it's hard to really pick one of these things out. The only definition I can see here is right here at E. You know that the definition of temp at this point is coming from up here. You don't also know the definition of x is coming here, but from the y, you don't know what the definition of y is because it might be coming from up here, or it might have been coming from the previous iteration of the loop of y. So you can see that available, or what one definition is there that you can go to, is actually very limiting, which is why it's an intersection, this symbol. The rest of the definition is pretty much the same. The availability minus the killing plus anything that's been killed, union with anything that's been created, and then exp where it's computed at n, and then kill is the same thing. Live is going to be a little different. Live is basically telling you what variables have been modified recently. So again, we're going to tell you what variables have been modification. So pretty much live out of everything before, live in, minus the killed, minus anything you've been generated, and generated used at n. So notice that the first line is not going to have anything live because it's a definition, it's not being used yet. But then later on, once it's modified, you can kill it, but gen is something that's used. So live is just telling you what variables have been used before you get to this statement. Going back to our definition, if we're on this line E, what variables have been used? Well, x, y, and y have been used, would be what's live here. Of course, when you jump back to the top of the loop, what's been used? Well, notice that live has been using a union, so it's possible that temp, x, and y have all been used at this point at a different iteration of this loop. If that's a little confusing, that's probably actually your best definition that I can give you. Another way to think about it is with this chart, which may be confusing to you, but that's okay. I gave you other definitions. Try and find one that's the most straightforward for you so you can get to knock out this homework. So forward or back, it's a node set, depends on its predecessors, aka before it forward, or its successor on the backwards. So in other words, and then any path / all node set contains a value if and only if it's coming from any or all of its inputs. All right, what am I telling you here? Forwarding, aka it's a predecessor, aka does it something to reach it for any path, that's a union. So if any path can go to it from before it, predecessor, then that's part of your reach. If all paths from predator can come to it, that's why it's intersection, then it's available. If something in the future at any path of the future actually modified it, then it's live. And then if something in the future of all paths did something to it, well, that's inevitable, hopefully. We don't have a good term for this one. This slide is just telling you what I said earlier. This is kind of an iterative process where it pretty much goes through your code more than once until it doesn't make any changes. So initialize the values, aka let's just take guesses. So any path, right now we'll say nothing, and for all paths we'll say everything. And then we'll just scan the code and see if we can update the any paths or the all paths, aka your reaches, your lives, and your availables. And if something changes, all right, go back to the top and check it again. And that's why I was talking about here, where the reach might just be this up here, boom, keeps going, and all of a sudden bounces back up and says, oh wait, we now know that there's a connection between here up to this while, so we need to update reach. That might happen on the second pass of the code. And then on the third pass, it probably wouldn't detect anything and we're done. Usually the more passes is how many nested deep your while statements are, or your functional analysis is, which we'll get to in a moment. But hopefully you can see that this iterative process of just scanning it with the reaches, the lives, and the available is definitely more efficient than trying to do that exponential search space that we were talking about earlier. But it's been shown it converges to a fixed point solution where new calculation produces the same values as the previous guess. And we're good to go. All right, work list. This is another way to go about it. Initial all nodes are on the work list and define values, default any path. Pretty much I think the previous one is the simplest or the easiest to work with. Now while it's not empty, pick any node, remove it from the list, and apply all your data flow algorithms. So this is just another way to do it. You have an empty list, you need to go to each node and do a full analysis. All right, eventually you'll become empty because you're always taking something out, and then the algorithm stops. Cooking your own. We can use the same algorithms to approximate other properties, the generation, the kill, the flow graphs, taintedness, aka when did it come from the web, at what point do we actually scrub this statement for an SQL injection. There are different ways to do this analysis. Hopefully you can see that most of these tools are usually modules that you can plug into that allow you to actually hook into this analysis and actually provide something back. All right, flow equations, yeah, they need to be monotonic. Okay, they're just saying they initialized at the bottom and they're always flowing towards something is what they're saying. Well, I call it power set lattice, that's fine. Monotonic y is always greater than x implies that f of y is greater than f of y. Knows that it's always increasing with the number of values. The point of here is just make sure that you're avoiding the exponential explosion. Because if you go from here to AB and then back to B, well, now there's tons of paths around here for only 3 values, namely 8. So we need to avoid all those selections. What else can be done with this? Well, what other type of analysis? Arrays and pointers do produce uncertainty, do different expressions to access the same thing. How do you know that a sub I is the same as a of k? Well, if you knew that I was equal to k, you'd know that. But you need to do some data flow analysis to actually know if those two variables are the same. Again, data flow analysis is important. Same thing as a of I is the same as b of I. Well, how do you know if a is equal to b? That's called aliasing. You got to do some data flow analysis in order to figure that out. The uncertainty is accommodated by depending on the kind of analysis, so doing on which type of analysis may generate or give you this information towards the end. Lastly, or at least I hope this is the last thing, we need to talk about basically what about going from different function calls, because that adds a new layer of complexity, as well as some cost and precision trade-offs that come with context sensitivity and flow sensitivity. So real quickly with the function, if you have a function, maybe it's inside of a loop sub and calls some other function returns, maybe this has another loop inside of it, you need to do that type. How are we going to do the analysis of that? Well, context sensitive, interprocedural, distinguishes a subcall from foo from a subcall in B, meaning that when you jump here, it needs to do redo the full analysis here. And the point of that is now you know what the variables are around the subroutine or the function. so you know what effect they're going to have on different values when they call sub, when you're calling sub here. Context insensitive does not separate them, could call sub, and sub could return to bar. Basically, the idea is that you really just want to do the analysis of this function and then leave it alone. The reason for this is if there's a side effect of the subroutine that may affect this of sub that may affect foo, and you want to do the context sensitive in order to figure it out, but the context insensitive will not figure it out. Hopefully your programmers are following good programming practices and there are no side effects here, but we're all programmers, so obviously the context sensitive is going to give you a better analysis, but this goes back to the exponential problem. Well, it's not actually exponential, it's in cubed problem, so it's a little slow to do this full analysis. Flow sensitive, intra-person, within cheap single or method, this fairly cheap for n cubed. So it's a slow, but it's not intractable. For inter, you can actually do a lot better, but it doesn't tell you what it is. Great. Okay. Quick summary. Data flow models detect patterns of your control flow graphs, nodes, initiating the pattern, when it terminates, when it changes. Often but not always about flow information. Dependencies is really helpful back for your static code analysis, so you can figure out things like SQL injection or other aliasing issues as well. Can be implemented by efficient iterative algorithms, so a lot of these code analyzers are actually fairly quick. They don't take that long in order to do the analysis. It's widely applicable, like with those static code analyzers I showed earlier. Limitation, it's unable to distinguish feasible from infeasible paths. It doesn't really know when you're going, the path may go into an infinite loop. Again, halting problem. Analysis spanning whole programs must trade off precision with computational cost. If you're going to jump from one subroutine or function to another, that does cost a lot more in order to do. All right, that's all for now. Let's go ahead and get started on your homework.